Okay, problem 6.1. The current is a 550 microhenry inductor is known a current in a 50 microhenry inductor is known to be this current going through it, this function. We're going to start with the first question, which is find the voltage across the inductor for time greater than 0. So this function of our current across an inductor for time greater or equal than 0. So you can go ahead and we know, well, let's move this here. We know that our equation for our inductor is going to look like this. T equals inductance times DILT over dt. Right? It's supposed to be an L. Okay. All right. So our DILT would look like this. So then we use the product rule, and we know that 18 times 8 to the negative 10t plus well, negative minus 10 t e to the negative 10 t. Okay. And then we can say this. So this shares 18 e to the negative 10 t 1 minus 10t. Right? So that is our DILT dt. Let me rewrite that. So okay. So then you know that our VLT, well, let me write that somewhere else. So continuing this, VLT is going to be equal to 50 E or to the negative 6 times 18 E 10 T 1 minus 10 T. You can leave it in that. Well, we can leave it in that form for now. So for question 2, I'm going to separate this. Problem 2 says find the power in microwatts. All right, so we have our function for, well, we know that power is equal to I times V. These are the only values we have. We can also make them different, but yeah, we know power equals current times voltage. So you can go ahead. We have the function for our current across the inductor. We have the function for our current or our voltage across the inductor as a function of time for both. So power at 200 milliseconds. So we can just plug this into the calculator. Times oops. And let's see what our result is. 18 times. So this is what I got for for the power, my calculator. Off this, we can solve for 3. It's asking if the inductor is absorbing or delivering power at 200 milliseconds. So since the power is negative, it means it's delivering power. Now it's asking to find the energy in microjoules of the inductor. You know that work is a form of energy, right? So our equation would look like this. For the energy inside the inductor. So and then at time we plug in this. And our result for that be so result for that would be 1.218 or 1.22. Here, that's where the so you got 1.21 or 22. If you want to round it, e to the negative 5 joules. Now it's asking for the maximum energy stored in the inductor and the time when that occurs. So go down here, make a little wall here, separate them. So the maximum energy in microjoules, or the maximum energy stored in the inductor, would be at when our DIL over dt equals 0. Because our current is our charge over time, and whenever this charge is, well, whenever the charge has its greatest, let's let's take the derivative of that. So, well, let's equal that to 0, sorry. So we got 18, say 18 e to negative 10t, I think, times 1 minus 10t equals 0. So we can bring this here. So we have 1, 10 equals 0. We know that over 10 is time at which I will be, or current where, or charge over time is going to be its max. So let's find the maximum energy. Okay, so yeah, this is the time at which energy is max. And so now we're going to plug this in to our current equation, which is, again, 18. Yeah, so negative 10 over 1 over 2. So that would be e to negative 1. So we get 0.66 amps, right? With this, it's the work equation, 1 over 2 L times I squared. .66 squared. And this will tell us the energy, the maximum energy the inductor will store during the frame that time, or yeah, during the frame of time that, or yeah, after t, or when t is greater than 0. Okay, so that is 1 over 2 times 50 e to the negative 6. 0.66. Okay, it's going to be a very small amount. Maybe 1.089 e to the negative 5 joules. Right, so it's asking us, what is it asking us? A microjoules. So microjoules, just move the decimal. You have e to the negative 6. 10 to the negative 6 is microjoules. So yeah, there we go. 10.89 microjoules is the maximum energy the inductor will store.